All right, in this question, question number 6, it reads, describe the IV characteristic of a metallic conductor at constant temperature. So remember that a metallic conductor at constant temperature is going to have it's going to obey Ohm's law. And so if we think about Ohm's law as something where the voltage and the current are in proportion, right? So when we divide voltage by current, we get a constant resistance. Well, if we plot I against V, we're also going to get sort of a constant sort of value. It's just that the resistance is the inverse of the slope of, I against V because of the way we sort of define it there. So an IV characteristic is plotting the current against the voltage like this. And we'd see that for a metallic conductor, it's just going to have something like this, where as the voltage goes up, so does the current. Those things are in proportion, so that we could sort of solve it there. So we just say, the voltage and the current are proportional. So there'd be a constant slope on the IV characteristic, right? And the inverse of that slope is the resistance. Those are sort of all the ideas there. A semiconductor diode, though, looks like this, completely sort of different. And so there's a threshold voltage that's usually around 0.6 volts. So at 0.6 of a volt, that's where it will start to sort of conduct. Before then, if we look at sort of the slope of this is basically 0. And if we take the inverse of that, we realize that the semiconductor diode has like an infinite resistance at these sort of low voltages. It's not until we get to the threshold voltage does it start to sort of climb up, or the resistance drops from infinity. And now if we were to take the inverse of the slope here, we'd have a value, that's not infinite. Okay, so it's sort of the semiconductor diodes don't conduct because they have infinite sort of resistance until you get to the threshold voltage. Their IV characteristic is not one that sort of obeys Ohm's law. Just like we saw how Hooke's law was only obeyed during certain parts of it. Well, this one, Ohm's law isn't obeyed everywhere, right? It's like, here is the part where it disobeys it. Now, once you get across that threshold voltage, it can start to act like a resistor R that obeys Ohm's law. We're like, okay, well now here the voltage and the current are in proportion, right? We could sort of draw a line right there. But this first part of it is saying that this is a non-ohmic component. So remember, the non-ohmic components are not going to have straight line IV characteristics. That's the key idea. Resistors are metallic conductors. They do. Non-ohmic components are going to be something else, like an NTC thermistor, right? Or a positive temperature coefficient, thermistor, thermal resistor, right? So it's going to change based on sort of temperature. Note that they told us at constant temperature. At higher temperatures, the resistance is going to actually increase, because the protons are shaking around, a lot. There's more kinetic energy. So the key idea here is that you describe the IV characteristic here as being not in proportion, right? But sort of climbing up, at the threshold voltage. That's where it starts to increase, from 0. So we'll see what the mark scheme says and see if that agrees. Again, kind of putting that into your own words there. Now we've got 2 identical filament lamps that are connected in series and then in parallel to a battery of electromotive force 12 volts and negligible internal resistance. So we don't got to worry about that. So we see 2 lamps in series. Now those 2 lamps are in parallel. Okay. The IV characteristic of each lamp is shown. Okay, so that's what it is. Note that a filament lamp, is it ohmic or non-ohmic? Well, it's non-ohmic, right? Because of this curved line. So in other words, here it's like there's a certain proportionality that seems like it should go like this, but then around here it starts to level off. So we could kind of say, well, it sort of obeys Ohm's law here. That's kind of like a line. This is kind of like a line, but it's the curve. And so this is a filament lamp as an example of a non-ohmic component, right? There's parts of it that may obey Ohm's law, but it is a non-ohmic component. Sort of operates on the principle of it's getting really, really hot, right? And glowing. So we've got the IV characteristic of each lamp, okay? And we want to use the information shown in the figure to determine the current through the battery in the circuit in 6.1a, and then the current through the battery in 6.1b. And then we're going to have to calculate the total resistance in the circuits both times. And then the ratio of the power dissipated. So that's all the work before us. Shouldn't be too bad. All right, let's see what we can do here. Perfect cooperation with the scroll bar as usual. All right. Yeah, what do we know here? Because these are identical, we know that a resistance is going to be the same. If there's 12 volts in, 12 volts out. Let's review all the physics, shall we? That's why we're here. The sum of the EMFs equals the sum of the PDs. That's Kirchhoff's second law. There's the sum of the EMFs, 12 volts. There's like maybe a 6-volt battery and there's another 6-volt battery. This symbol means there's a battery of cells, of electrochemical cells. And so the sum of our EMFs is 12 volts given. The potential differences are the voltage drops across the resistors. And if these are identical lamps, then the voltage drop is going to be the constant current that's the same everywhere times the resistance that's the same, right? V equals IR. So the voltage drops are going to be the same for this. If we know they add up to 12 and they're both the same, then we can pretty well deduce that the voltage drop across each filament lamp is 6 volts. No lost volts, right? Negligible internal resistance. And that allows us to really hone in on this point right there. So at 6 volts, now we can see what the current is. It's this value right here, right? So we have to sort of use this information to deduce the 6-volt drop across the lamp. Just dealing with the series circuit, right? The parallel circuit is going to have all 12 volts. So note here, we can read off what the current is. You know, that's kind of nice because it's right at 4. So we kind of know that when there's 12 volts, the current, you know, is 4 amps. So 4 amps, you know, sort of. We'll get to that. All right, so 6 volts. All right, and this one does intersect the gridding of the graph kind of nicely. So to get from 2 to 4, so 3 would be like right here. So it's going up by 2s, I think, 2.2, 2.4, 2.6, 2.83, 3.2, 4, 6, 8, 4. So 2.2 or 2.8 amps is the current that corresponds to 6 volts. This is the IV characteristic of the filament lamp, right? So it's just sort of telling us that. We want the current through the battery. So the current through the battery here is going to be 2.8 amps, goes through this, 2.8 times 6. That can't be right. Oh, wait. 6 is the voltage drop. We don't know the resistance yet. We could calculate it. All right, so that's good. We can deduce that 6 volts, you know, gives a current of 2.8, and the current is the same everywhere, right? So it should be that these 2.8 amps go through this, they go through this, you drop all sort of 12 volts, and then the 2.8 amps goes through the battery to get re-energized, you know. Remember what voltage is, it's telling us we're putting 12 joules per coulomb of charge. Right? So these 2.8 amps of current, that's the charge per time, go through the battery and they get another 12 joules, and then those 12 joules drops across it. The voltage is the same across parallel branches in a parallel circuit. And so if there's 12 volts here, then there's sort of like 12 volts between these nodes, and each lamp is connected across them. So there's 12 volts across each of these, which means the current through them is 4. Since we went over Kirchhoff's second law over here, let's go over Kirchhoff's first law over here. The sum of the currents in equals the sum of the currents out. So if we know that there's 4 amps going through here, and we know that there's 4 amps going through here, then there's 4 amps right there, and there's 4 amps right there, then how many amps are coming out? 4 plus 4 equals question mark equals 8 amps. So the current through the battery would be all 8 amps, right? So the 4 amps going through each lamp, combine 8 amps, and then the 8 amps right here split back up. So I like 2.8 and 8 for those two calculations right there. 2.8 and 8. You guys write it down because my answers on the screen are fickle and fleeting, and they will be gone. Look. So I think 2.8 amps for 1, and what did I say here? 8 amps, 8.0 amps, right? For 2. Total resistance in the circuits now. All right, let's go back up and work with our circuits up here. We want the total resistance in the circuit, each one. Total resistance. Okay. Total resistance. So V equals IR, or R equals V over I. And here I had a 6 volt, 2.8 amp. Here I had a 6 volt, 2.8 amp. So 6 divided by 2.8 is 2.14 ohms of resistance. I can just solve for R by using V over I. I know that there's 6 volts across each one. I know that the current through each one is this. And so each of these resistors must be 2.14. And the way to sum the series circuit is to just add the resistors. So I have 2.14 ohm resisting filament lamps. And so I'll double that and get the answer here. The total circuit resistance for this one, 4.3 ohms. Now, since I already know this is a non-ohmic component, it's not going to have the same resistance at every current, right? At different currents, it has different sort of resistances because it's not a straight line. So here I have to sort of calculate, just like I did here. There was 6 volts divided by 2.8 amps. Well, now there's 12 volts divided by 4 amps, right? And so that's going to be 3 ohms. So this is a 3 ohm resistor, right? So its resistance actually increases, okay? And that's like saying the steepness of the line here is shallower, right? So that when it was down there. So we're taking the inverse of sort of the line drawn tangent here. That's the resistance, right? So it's shallower here, which would be the inverse would be a sort of a higher slope. Let me show you more of the graph to really appreciate that. Because this is why we do these problem studies. It helps sort of emphasize the conceptual ideas here. So if we look at sort of what's happening to this curve here, this IV characteristic, if we drew a line tangent right here, right, that's just calculating 6 divided by 2.8. That's taking sort of the derivative right at that point, right? And so we're getting sort of, well, what is the resistance here, right? By taking the ratio of 6 by 2.8, that gave us the 2.14 ohms. So the resistance here is 2.14, but if we go further up here, well, now it's a shallower line, right? It's sort of the steepness of this is going down a bit. And so if this is a shallower line, when we take the ratio, if we did the slope, the rise over run, right, it'd be 4 divided by 12, but it's the inverse of that, right? And so the shallower sort of slope here, once we take the inverse, then it'd be 12 over 4, and that's how we got 3. So 3 is bigger than 2.14, and that's because on an IV characteristic, it's 1 over R that is equal to the slope here. And so the line sort of gets shallower as we get further up at higher voltages, and therefore the resistance increases. So that's really just kind of exploring the physics. What we need to do computationally is calculate the parallel resistance here. So 1 over the circuit parallel resistance is equal to 1 over like R1 plus R2. And so this is a third plus a third equals 1 over parallel resistance. 2/3 equals the reciprocal. So we need to solve for it. So the parallel resistance is 3/2 or 1.5 ohms. So 4.3 and 1.5. I like it. 4.3, 1.5. Okay, those are the total circuit resistances for series, for parallel, given that arrangement. So far, so good. Moving right along now, we've got the final calculations for this one. The ratio of the power dissipated in a lamp to the power dissipated in a lamp in the second one. So we want power dissipated in just a single lamp. And since they're identical, we sort of choose any one. So a ratio of the powers dissipated. Okay. So let's remind ourselves that these are 6 volts, 2.8 amps, and 2.14 ohms. Let's remind ourselves that these are 12 volts, 4 amps, and each one was 3 ohms, right? So that's kind of like the voltage, the current, and the resistance. The voltage, the current, and the resistance for each one. We want the ratio of the power dissipated in like 1 lamp here to 1 lamp here. What is power? Power is current times voltage. And remember Ohm's law, V equals IR. So let's plug in IR for V and get I times IR is I squared R. So that's also power. And let's remind ourselves that if V equals IR, then I equals V over R. So let's plug in that for I. So I is V over R. So V over R times V is V squared over R. And that's a good equation for power. So you choose the one that you like. And we're taking a ratio of one of these to one of those. So let's use, I like I times V, right? No exponents if we can avoid it. And so I would take the ratio of 6 volts times 2.8 amps over, let's do an IV over here. So there's I, there's V. So it's going to be 12 volts over times 4 amps. 6 times 2.8 gives 16.8. And that's going to be watts of power, right? A volt times an amp is a watt. Or you just say, well, the units of power are watts. And so I can trust that. 12 times 4 is 48. So I have 16.8 over 48, which is a ratio of 0.35. So let's go back down here. Put 0.35. That would be the ratio. 11 marks on this one. Let's see how many we would have earned. I feel pretty good about it. Go back to the mark scheme. 23. Question number 6. Okay, looks like right away. Straight line through the origin. Oh, we should have got that for a metallic conductor. All right. So straight line was important, but through the origin, they even underlined it. So I'm going to take that mark away. I wasn't mindful of that. Isn't it true that when the voltage is 0, the current should be 0, right? And so that's, metallic conductor. It should go through the origin, right? But then everything is in proportion, which means it's a straight line. 0 current for one direction. So negative VE. Negative, voltage up to 0 or a few tenths of a volt, straight line or positive gradient / increasing gradient, or positive. And again, this V here is that threshold voltage. So it has like 0 current, right? So it's sort of a flat line up to a few tenths of a volt. That's 6/10 of a volt. That's the threshold voltage. And then it's a straight line with a positive gradient or an increasing gradient. So that's where it sort of climbs up, and that's where it would start to, conduct. So I don't know if, it's human being examiners that read this and they can kind of look at the language of how you kind of put that. I think definitely if you don't say through the origin, if it's underlined, that's sort of feedback to say, oh, I got to remember that. And I didn't, right? So okay, come on, shall I get it together here? You missed a mark there. I feel all right about this one. You know, I worded it slightly differently, but sort of got the idea. All right, so current 2.8, 4 for each lamp. So we got 8 amps for that one, 8.8 for that one. Then we had 4.3 and 1.5 ohms, and then 0.35 for the ratio of the powers there. So everything looks good. You know, maybe those initial IV characteristics, something to brush up on. All right, well done.